Hello guys, welcome back to my channel. It's been quite some time that I have been able to do something for you, but now that I am a bit free, I can work something out. First of all, I'd like to congratulate all those who cleared CSIR NET JRF examination, and best wishes to everyone who is trying to clear this exam. I have decided to start a new series on climatology, and in that connection, today I shall be starting with the first lecture. Alright, so let us begin. So, first lecture for today would be insulation and heat budget. We all know that the uh, sun is the most important source of energy on the earth, and all the processes, whether atmospheric, oceanographic, weather, climate, everything is controlled by the solar insolation. So in this connection, I would start the first topic today, that will be an introduction to insolation and heat budget, and I shall be continuing this topic over next few lectures. All right. So as we all know that sun is the most important source of energy on the of all energy on the earth. This is very important. We have to understand that the heat is obtained from the solar input, but we have to understand that the sun, it gives us light, and this light gets converted to heat. So first of all, let us see what are the other sources of energy on the earth. So sun is the most important source of all energy on the earth. The other sources of energy, they include heat from other celestial bodies, interior energy of the earth, and the atomic energy released through the disintegration of radioactive elements. These radioactive elements, they are in the earth's crust. But an important point here is that this energy, which is from these three sources, is not of any consequence from the viewpoint of weather and climate. They are either too small in amount, or they haven't yet reached the earth to impact the weather and climate, which makes the solar radiation the only source of energy for atmosphere, oceans, and various life forms. Now, this solar radiation, it is dependent on these four important factors. First one is the distance between earth and the sun, which we all know that the light, it takes 8 minutes to reach the earth, approximately 8 minutes to reach the earth. So it means that there is some distance between earth and the sun. Then nature of the earth's atmosphere, which will include its gaseous concentrations, gaseous concentrations, then the density, then the layers of the atmospheres. All these are very, very important. Rotation of the earth on its axis, we all know that day and night, they are due to the rotation of the earth, and revolution around the sun, it means that the air. So how much light is coming on the how much solar radiation is coming on the earth is controlled by these four major factors. Now let us look at some facts. The distance, average distance between the Earth and the Sun is 149 million kilometers. We can write it as 149 into 10 to power 6 kilometers, or it can be rewritten as 149 into 10 to power 9 meters. Okay. An interesting fact here is that we know that the Earth's orbit, it is elliptical. It's not circular. It means that there are two locations and the Sun is at one of the foci of the ellipse. This is the Kepler's law. Kepler's law. So it means that when the Earth is closest to the Sun during the perihelion position, then its distance is 147.1 million kilometers, while when it is farthest from the Sun during the aphelion position, then it is having 152 million kilometer distance. So the average distance is 149, 150 million kilometers. Okay. Second thing, as I already mentioned, time taken by the light to reach the Earth is 8 minutes. So we can easily calculate the speed of light. C is equal to approximately 149 into 10 to power 9 meters upon 8 into 60 seconds. Alright. So we can then do the calculations. Okay. Look at this diagram. Here, according to the distance in the solar system, we can see how much time is the light taking to travel to the different planets. So here we can see that the time taken to reach Mercury is 3.2 minutes, Venus 6 minutes, Earth 8.3 minutes, Mars 12.6 minutes, Jupiter 43.2 minutes, Saturn 79.3 minutes, Uranus 2 hours 39 minutes, and Neptune 4.1 hours. So it's very obvious that the time taken by the light to reach the different planets will be dependent on their distance from the Sun. Okay. Next fact, how dense are the planets? Interestingly, Earth is the densest planet in our solar system. Alright, have a look at this chart. Mercury 5.4, Venus 5.24, Earth 5.51, Mars 3.93, Jupiter 1.32, Saturn 0.69, Uranus 1.27, Neptune 1.64. You all must be aware that these are the planets from Jupiter to Neptune. They are called as gas giants, while Mercury to Mars, they are called as the rocky planets. And interesting fact is that the average density of Sun is 1.41. Now my question to you all will be, try to find out why it is that the Earth has the highest density. Okay. Then the temperature of the Sun. So the temperature of Sun ranges from the surface, the Sun surface. So Sun surface temperature, we are not talking about its core. It ranges from 5500 to around 8000 degrees Celsius. The average temperature is 5777 degree Celsius. Okay. All right. Now the Sun is the source of radiant energy. Apart from radiant energy, Sun also emits corpuscular energy. You should read about the corpuscular theory of light. Corpuscular theory of light from Wikipedia or anything, then you will be able to know what does this mean. Now interestingly, the corpuscular energy, it affects the magnetic field surrounding the earth, and these basically are the proof that the solar insolation or the light that is coming on the earth consists of particles, and these particles, they are aligned according to the magnetic field of the earth, and therefore we see these auroras. Aurora is basically a light which it's a colorful light which you can see on both the poles. So we have two types of auroras. We have the aurora australis and aurora borealis. Aurora australis is the light over the South Pole or Antarctica. Aurora borealis is the these lights which are caused due to the magnetic field of the earth over the North Pole or the Arctic. Okay. So these are a few facts. Now another interesting fact is the solar wind or solar storm. We all must be knowing that sun is not only the source of light and heat, but it also emits several particles like protons, neutrons. All these are thermogenic neutrons. So these particles, these constant stream of particles, they create the solar wind, and the solar wind, it goes all across the solar system and it hits the different planets, and each planet has a different response to the solar storm or solar winds. Now the earth is the solar wind is mostly deflected by the earth's magnetic field. So it's a very important fact that the earth's magnetic field deflects the solar storm. Uh, Let me detour a bit. I don't know if you have seen this movie, The Core. This movie is about the core of the earth has stopped spinning, and that has caused a breakdown of the earth's magnetic field, due to which these solar particles and solar winds start to literally cook up the planet. So the scientists, it's a fiction story, they tried to restart the earth's core, the spinning of the core of the earth. So the magnetic field of the earth, it deflects the solar storm, otherwise everything on the earth will be burnt. Okay, and this is how it happens. In this diagram you can see that the solar flares or the solar winds, they are deflected by the magnetic shield, and some of which enters gives us the aurora oval at the poles. That is why those lights which I just mentioned about, they are the result of those particles being deflected by the earth's magnetic field. Okay, so these are a few facts about the earth. So basically, what is insolation? Insolation is the acronym for incoming solar radiation. We all know that the sun, it emits energy of varying wavelength. Now the wavelength of that energy which we can see is called as the visible light, and this lies between the long wavelength infrared and short wavelength ultraviolet rays. So if you see in this diagram, the ultraviolet rays, they have a smaller wavelength than the visible spectrum, which has a smaller wavelength than the infrared spectrum. So sometimes this question is also asked in an exam. Arrange the following solar waves according to the increasing or decreasing order of their wavelength. So radio waves followed by microwave, infrared, visible light, ultraviolet, X-ray, and then gamma rays. This is how the wavelength is increasing, and the energy is exactly opposite or inversely proportional to it. We know that energy is directly proportional to the frequency, which is inversely proportional to the wavelength. So, the energy of the visible light is more than infrared but less than ultraviolet waves. So, this visible light is basically an electromagnetic spectrum. This spectrum, you know, it is a part of the EM spectrum, and the Vibgyor, that is the 7 colors that we see, they are a part of it. Interestingly, this light which comes on the earth, out of which 77.1% is absorbed by the atmosphere. Not a percent, that is watt per meter square. So, these are the solar fluxes. We will see in a few minutes about these values. Now, the Earth's energy budget describes the various kind and amount of energy that enter and leave the Earth system. So, energy budget means there has to be an account of the energy that is coming in, amount of energy that is absorbed, and amount of energy that is radiated. This is very important. Not all the energy of the earth is absorbed, not all the energy of the coming on the earth is radiated. So, basically the rays of solar spectrum reaching the earth's surface, they are converted to long wave radiant energy after absorption by the surface. So, if this light is coming on the earth, it comes in form of the electromagnetic spectrum, simply light, visible light. It is then absorbed by the surface and then converted to long wave infrared rays, which are then radiated back into the atmosphere. This is the phenomenon which converts the light into heat. This is a very common thing which you all must be knowing. Now, how much heat is coming on the earth? What are the factors that are controlling the light that is coming on the earth, and what is the earth's heat budget? For that, first of all, an important factor is the solar constant. So, 1368 watts per meter square means that on every square meter, if this area is 1 meter square, the amount of solar insolation coming on this, the energy that is coming, that is falling on this area is 1368 watts. Now, how to calculate this? How to calculate the power of the sun, and how to calculate the solar constant? For that, you have to keep in mind the Stephen Boltzmann law. Stephen Boltzmann law. What does this law state? This law states that the energy is equal to the Stephen Boltzmann constant multiplied by the fourth power of the temperature. Okay. So, if we have to calculate the power of the sun, that is PS, then PS will be equal to sigma T to the power 4, where sigma is the Stephen Boltzmann constant and T is the average surface temperature of the sun. Now, here this the value of sigma is 5.67 into 10 to power minus 8 watt per meter square Kelvin to the power 4. So, here power will be equal to, and the temperature of the earth's surface is, as I had already told you, 5,777 Kelvin. So, it is 5.67 into 10 to power minus 8 watt per meter square Kelvin to the power 4 multiplied by 5,777 to the power 4, that is Kelvin. So, this Kelvin will be cancelled out here, and this answer would be 6328 multiplied by 10 to the power 4, which is equal to 6.32 into 10 to the power 7 watt per meter square. Means from every square meter of the solar surface, this is the amount of energy that is being radiated. So, this is per meter square. So, what will be the total power of the sun? Total power of sun will be equal to this amount, that is PS multiplied by the area of the sun, area of sun. So, sun is a sphere, area of a sphere is equal to 4 pi r square. Okay. So, here PS multiplied by 4 pi r square. So, this will be equal to 6.32 into 10 to the power 7 into 4 into 3.14 into, now the radius of the sun is 6.96 into 10 to power 8 meters whole square. So, the total power of sun would come out to be 3845 into 10 to the power 23, or 3.845 into 10 to power 26 watts. So, this is the total power of the sun. Now, let us imagine that we are looking at the solar system. Okay. Now, let us think that this is the sun, this is the sun, and this is the Earth's axis. Let me draw it properly. If this is the sun and this is the Earth's orbit around the sun. Going this way. Okay. Let us now imagine that this is making a sphere. The Earth is making a sphere on the course of its revolution around the sun, this way. So, here if we are able to see through it, so this sphere of influence, of solar heat on Earth, that will give us the solar constant. Now, if we look at the previous slide, here we found out that the total energy of the sun is 3.845 into 10 to power 26 watts. So, let us write it here. P sun is equal to 3.845 into 10 to power 26 watts. Now, we have to calculate the amount of heat which is being transferred to the Earth. So, this is the Earth during the course of its revolution. So, the heat P sun to Earth will be equal to power of the sun divided by the area of this sphere, of influence, which will be 4 pi r square. Now the distance, this r will be the distance between earth and the sun, distance between earth and sun. This distance is 1.496 into 10 to the power 11 meters. So if we calculate it, it comes out to be 3.845 into 10 to the power 26 divided by 4 into 3.14 multiplied by 1.496 into 10 to the power 11 square. You calculate it and it would translate into 1368 watt per meter square. This value is the solar constant. Solar constant. Now, why are we calling this as solar constant? Because this energy is fixed. Per meter square on the earth is getting this much amount of energy. That is why it is called as solar constant. So to calculate this solar constant, you have to understand two things. First of all, that the since the earth is going all around the sun and it is tilted, there is a latitudinal distribution. So each point on the earth will receive the energy of the sun in some amount or the other. And you have to calculate it by using the sphere of influence, not the distance between the sun and the earth, but sphere of influence, because the earth is going around the sun during its revolution process. Okay, so this is how we calculate the solar constant. This is the value of solar constant. Now that we got the solar constant, let us see how much energy is intercepted by the earth. So if let us say that this is the sun and this is the earth and this is the earth. So if we look from the sun, earth would look like a disk which is intercepting its light, and the radius of this disk will be equal to the radius of the earth, RE. Now that we have the solar constant which is 1368 watt per meter square, let us see how much energy is intercepted by the earth, the total earth. So E intercepted will be equal to solar constant multiplied by the area of that disk, this disk, that is pi r e square. This comes out to be 1368 into 3.14 into 6370, that is the radius of the earth. What is the radius of the earth? 6370 kilometers, or we change that to meter, into 10 to power 3 whole square. This comes out to be around 174 into 10 to the power 15 watts, or it can be written as 174 petawatt. 1 petawatt is equal to 10 to power 15 watts. So the total energy intercepted on the earth is 174 petawatts, which is a huge amount of energy. Now, but we all know that earth has, we all are aware that the earth has reflectivity, also known as albedo. Albedo is the property of an object to reflect the light falling on it. So the highest albedo is shown by ice or snow, followed by the we have the water, then tree canopy, then we have the land also. So all of these, they have different albedos. The average albedo, the average reflectivity average albedo of the earth is 0.30. So, if we assume that the amount of light coming on the earth is also being, some of energy is also being reflected back, then how much energy is absorbed by the earth? So, this is the intercepted energy, amount of energy absorbed, it will be equal to solar constant multiplied by 1 minus albedo multiplied by pi r e square. I hope it makes sense. So, put in the values and you will be getting a different value of how much energy is absorbed on the earth. Now, let us now also find out how much energy is radiated, from the earth. So, radiated is equal to, again we have to apply the Stephen Boltzmann law, sigma T to the power 4. So, it would be 5.670 into 10 to power minus 8 watts per meter square, which will be multiplied by the average temperature of the earth to the power 4. So, this will be the energy radiated. We will not solve it right now. Let us look at a few more things. So, this energy radiated, it tells us that how much energy will be emitted by the earth per unit area. So, if we get that this much energy is being radiated per unit area, then the total amount of energy that earth will emit will be equal to E radiated multiplied by, now area of the earth, 4 pi r e square, because earth is a sphere. Now, we cannot use that disk concept over here. So, this will give us the total amount of energy. We multiplied the energy radiated per unit area multiplied it by the total area of the earth. Previously, we had calculated how much energy is absorbed by the earth. So, according to the law of conservation of energy, if we apply over here, law of conservation of energy, according to this energy, the total energy absorbed by the earth should be equal to the total energy emitted by the earth, which means that solar constant into 1 minus albedo into pi r e square is equal to the sigma T to the power 4 multiplied by 4 pi r e square. I hope you understand this. So, this cancels out. So, we get K s into 1 minus albedo is equal to 4 sigma T to the power 4. So, if we solve for the temperature, T will become the fourth square root of K s into 1 minus albedo divided by 4 sigma. So, this is how we can find the temperature of the earth. Sorry, I will add more slides to it. All right. So, now that we have got that T or the temperature of the earth, it will be the fourth root of Ks, that is the solar constant, multiplied by 1 minus albedo divided by 4 sigma, that is the Stephen Boltzmann constant. So, if you have all the values, we can put it as fourth root of 1368, that is the Stephen Boltzmann the solar constant, multiplied by 1 minus albedo will be 0.7, 1 minus 0.3 divided by 4 into Stephen Boltzmann constant, that is 5.67 into 10 to power minus 8, and if you will solve for it, you will get an approximate value of 253.7 Kelvin. That is the this is the predicted temperature of the earth, predicted temperature. So, if we convert this value to degree Celsius, so degree Celsius T degree Celsius is equal to T Kelvin minus 273.15, it will be minus 19.5 degree Celsius. So, interestingly, according to the calculations and everything, the predicted temperature of the earth should be minus 19.5 degrees Celsius, which should be way below the freezing point, freezing temperature of water. But we all know that the actual global average temperature is 14 degrees Celsius, which means that it is approximately 34 degrees Celsius higher than what is predicted. So, any guesses why the average temperature of the actual temperature of the earth is higher than the predicted temperature? It means that there is something on the earth that is trapping the heat. There are some entities on the earth that is trapping the heat and warm up the earth. So, guys, can you all guess what that could be? So, if anyone of you have guessed this, then you are perfectly correct. So, we just proved that how this greenhouse effect is actually keeping the earth warmer than it could have been. It could have been well below the freezing point of water. So, no life, no biological activities on the earth. But this greenhouse effect, how important this is for earth to keep the activities going. So, for start, this is enough for this lecture, and I shall be continuing with this. Slowly we will be catching up on the other aspects of climatology. Guys, if you like this video, give me a thumbs up, and do ask me questions, do point out any queries if you have. Okay, so I hope you all enjoyed this lecture, and we will be meeting soon. Bye bye.